Thanks for everyone for coming today. It's my great pleasure to introduce and to have as our guest Carl Boettiger. Yep. From UC Berkeley. I've actually written a couple of notes about Carl's background, which is tremendously impressive. So Carl earned a Bachelor of Arts degree in physics at Princeton University before doing his PhD under Alan Hastings, PhD in population biology with Alan Hastings at the University of California at Davis. Then he went on to do a postdoctoral research fellowship, NSF postdoc fellowship with Stephen Munch and Mark Mangal at UC Santa Cruz, working on fisheries related problems, among other things, I believe. And Carl is currently an associate professor at the University of Berkeley, and he's also recently been the recipient of a prestigious NSF Career Award. So Carl works on problems related to ecological forecasting and decision-making under uncertainty, particularly in the context of global change, conservation, and natural resource management. And with that, I'll hand you over to Carl. And yeah, welcome, Carl.
Thank you. I'm going to talk about conservation decision-making at the limits of prediction. So why conservation decision-making probably needs no introduction. We're all aware of the many challenges that face our environment, from climate change to increased risk of forest fires we experience in California as much as you do, to global fisheries declines and overfishing, to the production of food supply and the agricultural transformation, introduction of an invasive pest like the pine bark beetle here that's responsible for this massive forest devastation in the Northwest, to, of course, COVID and emerging diseases. The question, of course, is what do we do about it? Well, I'm going to posit that we already have the answer and it's wrong. Yes, let's make that go away. You see that? Let's see. One moment. Beautiful, much better. Okay. And that is that we need prediction, that we need to sort of look into the crystal ball as scientists, provide the crystal ball to tell the decision makers what the future is going to be, and then they will figure out what to do about it. And I think that it can be very compelling, but it is not enough of the story. So we're going to focus on the decision-making problem as a science problem. So why do I say that? This talk will be divided into sort of 3 chapters. In the first, I will argue that better forecasts do not necessarily make for better decisions. All right, first, forecasting itself is a hard problem. It's a rich problem. I won't be talking about our forecasting work in this talk. We're going to focus on decision making, but I just wanted to nod to the complexity of ecological problems. We know from weird things that ecology can do, from oscillations to tipping points to chaos. It's very hard to predict, and yet very important to understand what is going on in the future. And yet we actually don't make predictions very often. We predict only things that we already know. So unrelated to this, but talk, I did want to highlight recent work we have in the forecasting initiative, where we're trying to get ecologists to actually predict the future before it happens, before the data is collected. And so we have this ongoing challenge to do just that. So while this talk will be somewhat pessimistic about prediction, I think it is an important part of testing our understanding, and no better way than to make scientists actually state their predictions before we get measurements, and then see how well we do and see which models are doing the best. And so this is the Ecological Forecasting Initiative is doing just that in these 5 themes. We have over 50 teams submitting now their predictions every week that are trying to predict future measurements of data collected by NEON, the North American National Ecological Observatory Network. We've just launched a similar program with some of the TURN data, so we're hoping to have a more Australian flavor to that soon. Okay, but the problem gets worse than that. Even when we have good predictions, they can lead us astray. So my overall premise in this talk, which you're going to see run throughout these 3 chapters, is to sort of understanding the value of models as a heuristic tool. And there's this fantastic quote I like from a recent paper by Schindler and Hilborn, just pointing out that the primary value of ecosystem models are precisely that, a heuristic tool for communication and developing different scenarios to express uncertainty and test policies. Reliable forecasts will remain elusive. So it's a heuristic tool, it shows uncertainty, it tests a policy. We'll talk a lot more about testing a policy in the second half of the talk. It's not to provide just a quantitative prediction of exactly what will happen. In fact, you can find earlier arguments for this point, the idea that in fact, we never demonstrate that an ecological model is true. So much of our ecology is talking about, do I have the right model? Do I have the better model? And it's important to keep in mind that it is a mathematically impossible thing to state in an open system that you have the correct model. Quoting Oreskes from 1994 in Science here, verification and validation of numerical models of natural systems is impossible. Such systems are never closed, and therefore their results are not unique. We'll come back to the importance of that. So their predictive value is open to question, but their primary value is heuristic. And we'll get a more concrete meaning of what it feels like to be heuristic value in a moment. In fact, I found an even older reference all the way back to the Third Age of Middle Earth that Galadriel is said to have mentioned that models only show what might happen, for even the wisest cannot tell the future. The model shows many things, things that were, things that are, and some things that have not yet come to pass. We will see this example in a case study using fisheries management, in which I will show that of the models we consider, the one that appears to be making the better forecast is leading to worse decisions. And we will unpack why that is and change sort of the purpose of why we're using models and when we have enough. So how do we choose models? Of course, the classic science answer is you just compare whatever your alternative model is, and we don't say too much about where it comes from, to our available data to choose a model. It goes something like this. Which model is producing the better forecast, the better prediction? I have two models, model 1 in blue, model 2 in red, and I'm comparing them to real data. As you can see, model 2 is always spanning the data as we would hope. They've got uncertainty in them like any good model should, and model 1 is nowhere close to the data. So which model is going to produce the better forecast? All right, well, in that case, I was just comparing the model's prediction to data, but I wasn't making any decisions with the model. What happens if I actually do what the model says, use the model to predict the future stock size of the fishery, harvest according to that prediction, set the fishing quota according to that prediction, and that influences the future value of the model. We can see that in this model 2, it's controlling the stock size consistently at some fixed value, and it's consistently making predictions that match up with its own expectations. So I get different outcomes under model 1, but they are still off. So whether I'm using the model to make decisions or I'm just using the model to make predictions, model 2 is doing better. But if you squint at this, you might notice the stock sizes of this rather over-optimistic model 1 are actually a bit larger than they are under model 2. If I say what model is boosting a better forecast, not just in terms of the dot is within the uncertainty, but in terms of a very rigorous standard of a strictly proper score. A strictly proper score has this wonderful property that if you have the true model, no other model can do better than it, right, in a prediction. So you can't overfit in terms of proper scores. So when you score forecasts, you do competitions, you ought to make sure that you're using metrics like a log skill score or a CRPS score that is a proper score that has this property. People often do forecasts that don't have that property and they can't overfit. So, but we can in this sense, again, reject model 1 and say model 2 is the best proper score. Let's look at terms of the decision outcomes of managing under each of these models. So here, model 1 has this higher ecological outcome, the state is higher. And model 2, now that you see them on the same plot, you can see is quite a lot lower in terms of the total stock size of this fishery. But more surprising is the economic outcomes. Model 1 is producing more economic value than the far more accurate model 2. So in either case, model 1 is doing better. Now, what do I mean by sort of making a decision with their forecast? I am literally taking their forecast, writing down a transition matrix. These are all of the possible values you could go to, putting this through a stochastic dynamic programming algorithm and determining the optimal policy given the model. Now, of course, how does this happen? The true model is neither model 1 nor model 2. In fact, because we never know the true model. The true model is always more complicated than the models we're using to make predictions. That's the whole purpose of modeling. That's why we call them models. So what has happened by choosing the model that's making the better prediction? We have this red line where we're lowering the stock sizes and we're overexploiting the population, and yet we keep getting predictions that match the predictions of model 2 of that red model. They keep rejecting the blue model, and so we're convinced that we are right. How does this happen? Well, if I plot the growth curves of all 3 models, in this case, I'm using a simulation study so we can explore, and so the true model can be known to us. In reality, of course, it never is. It's in green. And I have model 1 and model 2. you can see that whichever model is closer in state space, the curves are literally closer, is the model that's going to make better forecasts. And model 1 is vastly overestimating the growth rate, so it's making terrible forecasts. However, if you recall your optimal control theory from Gordon and Schaefer and the 50s,
should I go into D?
you'll know that the optimal harvest rate in this particular fisheries problem is to harvest at the rate that the population is growing the fastest, right? The optimal decision is right here, right? If model 1 is true. If model 2 is true, the optimal decision is this much lower stock size. And hence the reason that when I manage under model 2, you saw it holding the stock size at a low value and at model 1 holding the stock size at a high value. In fact, how big, the prediction of the actual growth doesn't matter. The only thing that matters for the optimal decision turns out to be what is the location of the maximum growth rate. And of course, this true model, which is asymmetric, has its maximum growth rate at the same as. This is that degeneracy I was talking about, that there are multiple decisions, that the optimal solution for the true model is not unique, right? That there are other models that have that same optimal decision. So how does this problem happen that we choose the wrong model? Ultimately, this is a problem not of our approach in model selection, but models we began with in the first place. We have too few models, and they're all quite simple models, so they don't capture the space of real possibility. And therefore, a quite simple wrong model can have a better policy than a quite simple, than another quite simple model that's giving much better predictions. So this returns us to our conclusion: models are heuristic tools to express uncertainties and test policies. Here, more models to express more uncertainties, and then we can see which policy the best. We don't actually need an exact prediction to make a good decision. We just need to know what is the right stock size at which this overall fishery is most productive. And the rest of it is more complex than we need. All right, so I'm going to move into part 2. Yes. Yeah, if you're online, can we just, we're picking up some of the discussion, so please stay muted. Thank you. All right, part 2. Decision under uncertainty. Okay, so we can see the different sources of uncertainty entering into a decision process. I have so far talked about some of the different models. We're going to come back to that. I want to go into the sort of 3 ways you could describe uncertainty underlying a process. We could say I have stochastic, the underlying process itself has uncertainty. I can have imperfect observations. So even when I know the right model, I don't get exact measurements of the real world. I just get partially observed measurements, or I get measurements with error. And also, I don't know what the true model is. So we have all of these problems we have to deal with in making decisions at the limits of prediction. So first, classic optimal control that we have just seen within the fishery says, if I know that curve exactly, if I know those curves, I already pointed out that we would harvest those populations down to their most productive level, their biomass at maximum sustainable yield. So this is just showing that same decision problem, but I've switched my axes from stock growth rate to this escapement term. This is the biomass minus the harvest. So it's a 1-to-1 line, meaning don't harvest up to here. And then after that, you always harvest the population back down to that biomass. That was the deterministic solution. What if we add more uncertainty to it? So we saw that first, by about 30 years after the original theory was developed, Reed pointed out that the stochastic solution, if you add uncertainty to that problem, you don't say that we know that the population always follows that deterministic curve. In fact, it doesn't change the optimal strategy at all. What I told you about always just harvesting straight down to the biomass at maximum sustainable yield is exactly the same in a stochastic case as a deterministic case. So this caused a couple of people to scratch their heads. So they said, oh, it's a proof, right? It's a process uncertainty is taken care of. Stochasticity doesn't matter. And that seems strange, right? Because we think that as uncertainty increases, we should probably be more cautious. And it took a couple of years before researchers started really questioning the results of Reed's paper and pointed to several reasons why this kind of result was counterintuitive, why uncertainty didn't matter and you could just do the deterministic thing in this decision. They said an important tacit assumption that Reed is making, as in other works that have been doing this blah, 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 is that the level of the stock size is known right before you make the decision. So even though it's stochastic in growth, you get a perfect observation. and you know the stock size without any error, and therefore you know a safe amount to harvest. You can't accidentally say, oh, I thought the stock size was big and I thought I wouldn't crash the population. So they say this must be the key problem. You never know that, and if you took that perfect measurement away, maybe we would find that stochasticity uncertainty matters and you should be more cautious. So they did this. They just reversed the order of those two things. They let the recruitment occur first, and then you have to, before you measure, choose how much to harvest. And they actually get the opposite result. They find that instead of being more cautious because there's uncertainty, you in fact become more aggressive. You harvest more. Here's the constant escapement solution. Here's the highest uncertainty result. And they say you should actually overfish this population more with measurement error than if you had perfect measurements. They wave their hands. They point to the fact that this seems counterintuitive. But, we're quite good at doing this in papers. The more you stare at a result as an academic, you can explain anything. And so they have a good long discussion section in which they can convince themselves that this counterintuitive result is actually correct. By 2005, Chris Costello and Sethi Gautam and others were looking at the same problem and saying, we really don't think Clark and Kirkwood closed the book on that. Their introduction of uncertainty was somewhat crude. They just said the uncertainty comes by that one switch. You still get a measurement with perfect data, but then you have 1 year of stochastic growth and you have to make your decision. But in reality, you never get that perfect measurement. So they said, let's do the problem more thoroughly, right? And we'll say that after each measurement, you say there's uncertainty from a probability distribution, and they look at the math and they say, doing this is a little bit difficult. Let's just, instead of propagating that uncertainty, we'll just default to the prior. We'll say that after each measurement, you say, my prior probability of the stock size up until this point is just uniform. And by that simplifying assumption, they're able to do the math as well. And lo and behold, they get an even more extreme result than Kirkwood, saying that you should harvest with measurement uncertainty a lot more than if you had no measurement uncertainty. Again, counterintuitive, right? We think uncertainty, precautionary principle, and yet they're saying no measurement uncertainty would actually harvest less than measurement uncertainty. And again, you find the same discussion, right? This seems counterintuitive, but there's plenty of text in the discussion and they convince themselves that this makes sense. You can note, as I just pointed out there, that they point out only kind of as an afterthought in the discussion that when we say optimal policy, we had to take a shortcut. They said the manager uses only the current measurement when forming expectations, right? Only the most recent measurement. Now, the technical correct thing would be that all of your past measurements should inform your current expectations of the stock size, right? But that's mathematically complicated. So maybe it's safer to ignore that. We find that this is actually going to change the results quite significantly. So they say the optimization problem for doing the full thing, it's complicated. We took a shortcut. Meanwhile, over in computer science, the same problem has been studied for about half a century. And by the early 70s, they already knew in theory how to solve the full problem that Sethi is saying is too complicated. They knew in theory, right? And this beautiful paper came out from Smallwood and Sondic saying the optimal solution happens to have this nice process in which you can assume that it's this piecewise linear convex function. This is right there in the abstract, right? It took them another like 30 years or longer before they could make algorithms that could exploit that piecewise linear convex element to look for the optimal solution in the full space of the partially observed problem. And eventually those things got numerically fast enough that we could try them on a large problem like fisheries. And so we're able to kind of pick that work up from the computer science and bring it back to fisheries. A nice fact is that if you go back to the really early start of this kind of optimal controls in the computer science literature, it's actually starts almost the same year as the fisheries optimal control and refers to some of the same problems. But they went off to do self-driving cars with that. So this paper by Lee and others, and then this is the DARPA challenge. That was one of the early examples of a paper using the full POMDP solutions. They were worried about robots. We're going to bring the robots back to the fish. That will be a theme that we'll see again. And so just to close on that story is that we are able to, once you track the uncertainty the way you're supposed to, you don't make the assumption that you only use the most recent information. You can discover that, in fact, your intuition was right all along, that the precautionary principle does apply. in general, you should be more conservative. You should leave more fish in the sea when you're uncertain. It doesn't happen in all cases. If you have seen years and years of a high stock size and you get one really, really low measurement, you might be like, well, maybe that's just measurement error. But if you have seen many, many years of low stock sizes and then you get one measurement that's a lot higher than that, chances are that's just measurement error and you should indeed be more cautious. And so the full numerical POMDP solution lets you track that. And this difference matters, by the way, so we could revisit this famous paper in Proceedings of the National Academy that Costello and colleagues did, pointing out that while business as usual would deplete stocks, if we simply do what they call constant mortality, this FMSY policy, we could still rebuild stocks. And if we do this constant escapement policy, which they call rights-based fisheries management, we would rebuild stocks even faster. This is the solution, the bang-bang solution, ignoring measurement error. And in fact, if you ignore measurement error in a situation where there really is no measurement error, that's true. As you add this measurement error, that MDP solution, that bang-bang solution gets worse and worse. By 20%, you actually would do worse than business as usual because it's so aggressive, right? It says if I have perfect information, I can harvest directly down to that stock size. And so this is across about 400 different stocks in the RAM legacy assessment database that all lead to overharvesting. Okay, great. So we can do observation uncertainty, but what we really want to do is get back to model uncertainty. We want to say, I don't know the true model. I want to do better than just writing down sort of the two logistic curves that we saw in model 1, model 2, and choosing the wrong one. So how can we take account of the fact that we don't ever know the underlying process at all? That POMDP work, we got to put an observation uncertainty. We still had to say we knew the process model itself. Okay, so this is a chicken. The chicken's going to make decisions. Can we make decisions without a model? I want the chicken to peck the dot of my choice, right? In this case, the pink dot. Can I train the chicken to always peck the pink dot? It doesn't predict where I'm going to move the colors. It doesn't have to predict the future at all. The chicken is purely reactive, right? I train the chicken by giving it a reward. When it does the action I want, I give it a positive reward. It gets some seed. If it pecks the wrong dot, it doesn't get that. And the chicken is a very good reinforcement learner, and it very quickly learns to do this. It's easy to forget this lesson as we get better and better at building ecological models and more complex models. We can make decisions without models, right? Well, can we do this in fisheries? All right, we have the chicken. So in computer science, and actually also in behavioral ecology, this process is called reinforcement learning, what the chicken is doing. The chicken observes its environment, and it gets a reward from its environment upon taking an action. And it just iterates on this process, and very quickly it learns how to associate certain actions with better rewards, given certain observations. People noticed this worked with chickens, then they noticed this worked with robots in the 90s. This was an early robot trying to learn how to move, and it knows nothing about its motors, what's available to it. It just starts moving its motors at random, but it has a reinforcement learning algorithm to update how it should behave. And after trying different behaviors at random, it's given sort of an electronic reward for moving to the left. And this was a nice early example where it really learns this kind of very organic way of kind of almost like a worm kind of inching to the left and getting a reward without being told anything about its world, about motion, about the laws of Newton or anything. This approach has become popular in recent days. So here's some recent covers from Nature and Science, all using reinforcement learning to solve cutting edge problems and to perform in decision space using algorithms that can outperform the decisions of human decision makers. So this example in playing Atari games in 2015, the agent had to learn across the full space of all of the Atari games how to play the game just by trial and error, playing the game iteratively, and be able to generalize what it learned on one game to a game it's never seen before. Such a system was all similarly applied playing Go, playing chess, playing a combination, the same agent learning to play Go, chess, and Shogi. To controlling StarCraft 2, there's a nuclear fusion example that recently came out the same year as this Nature paper with the driving cars, Formula One racing cars. And the chat part of ChatGPT is also trained with a reinforcement learning algorithm using human feedback to determine some of the reward values. So there's a lot of recent development in these algorithms. Maybe they're good enough for us to bring these over to fish. Just to get us sort of a feel for what this looks like. This is the sort of robot or training process where it's most often been applied. As you saw, all those examples kind of come down to either robots or computer games. And so hopefully the world's more complicated than just that. This is a robot learning to complete different race courses, and it's doing this by that same feedback process. So here it's been trained on these varying environments, including environments that it's now can be presented to that it's never seen before. It doesn't know anything about the laws of physics in the beginning. It just has to experiment with its different options, with its different actions it can take, and it learns to kind of make decisions in a complex environment. Oh, that's kind of similar to what we want to be able to do in ecology, right? We want to be able to do in decision problems. We want it to be able to generalize as well. So this is the Atari example. I've grabbed a screenshot of several of the games the Atari agent had to learn. You didn't want it to just learn how to play one game. It turns out you get the exact same overfitting problem that you would do with traditional model fitting. If you learn only one game, it can play that game really well, but if you change any small aspect of that game or give it a different game, it fails. But if you force these agents to play enough different games, they learn more general rules, and they can therefore then perform in environments that are novel, that they've never seen before. So in the RL space, that's called transfer learning. And it's the same challenge we have in the real world, right? That we want things not to just work for our ecological models that we make up, but for the real world as well. Okay, in order to do this process, we need mechanisms, right? So we have a model-free agent. The agent isn't predicting the future, it's just learning what to do. But we still need a model to simulate the environment. So the model mechanism part goes over here. And the nice thing is that we don't need just one, right? So going back to that earlier result, that models are heuristic, they're used to explore possible policies. We don't need to say, I know this model is what the real world looks like. All we need to say is, this is a plausible model. If your agent can't make good decisions in this model, it probably can't make good decisions in the real world. And we don't need just one of them. We can make as many of those simulations as we like. And we want to train our agent to deal with all of those possible worlds, to have good intuition, to make good decisions. All right, so can we do this? We're going to start with a fishing example. So can we do sustainable harvest without models? We're going to write lots of different models. I think I have a bit of feedback. We can write down these models as simulators, but then the agent doesn't get to see what's under the hood, doesn't get to know the transition probabilities, has to learn how to make decisions. So in classic machine learning style, you can make a leaderboard of many different agents. We can start with known problems like the constant escapement or maximum sustainable yield case. And here I've rescaled everything to the solution of the constant escapement. You can see maximum sustainable yield is getting only about 59% of the constant escapement, which is optimal in this case. It's always good to use a known reference. Here, this algorithm known as A2C, an actor-critic algorithm, is getting almost equivalent to the maximum escapement, to the constant escapement solution there. So at least in models where we know the answer, this works. Not all of the methods work. Some do okay, 98%. Some are doing considerably worse. So they don't all work. That's important too. And we'll come back to that theme. But we can, at least in principle. You can test this in historical data in only sort of loose fashion, right? Until someone will let me actually make decisions in a real fishery using my AI agents, the best we can do is look back over history and say, would the algorithm have made different decisions than we made in the real world? So this is where we overfished Argentinian hake in the early 90s. And you can say, this is what the actual historical harvest rates were. And the algorithm would have been far more conservative. So this doesn't tell us all that much, right? It tells us the algorithm went something too stupid, at least. It would have said, stop harvesting, given this information. So this reminds us, like models, or in this case, environments, are just heuristic tools to express uncertainties, right? We're expressing any of these things might happen, and let's test our policies. To do this, we need lots of plausible environments. We don't actually have that many great models of ecological processes in all their complexity yet. This was an interesting paper from Mark Urban and colleagues last year saying we really need to build a lot more models with a lot more complexity. But the nice thing about the reinforcement learning approach is that we're allowed to at least decouple the process of defining our model from the constraints of solving that model. So often in modeling, we say, I need to choose a simple model, not just because I believe that a simple model ought to be sufficient to explain the complexity of ecology, but because it's tractable, right? Because it's suitable for my methods, right? The RL agent doesn't care, right? It just wants a computer game, and the game can be basically as complicated as you want, and it's just going to try to learn something. So this is a decoupling of that, and we need more such simulators. Here, we try a more complex model. So this is, instead of the one-dimensional fishery, we say, let's consider where there are 3 interacting species, and they're interacting in such a way that I know is going to create a tipping point in the dynamics, right? That if you cross a certain threshold, the fish population will collapse, and it will be stuck in a low population state from which it's very difficult to recover. So a much more challenging management scenario than the simple case of the single species logistic curve. Also, I have a more rich control space. Maybe I'm not just looking for the actions on a single species, but I'm harvesting 2 different species that are, in this case, in apparent competition with a single predator. So I can take such an environment and I can say, what if I do sort of classic control? How do we approach this problem today? We approach the problem today by saying, I must propose a policy in advance. This is the Schindler and Hilborn idea, right, of saying, you say, this is my policy, I can test a policy, but we can only test relatively simple policies, right? You can say, try harvesting at a mortality of 0.1. Then try a mortality of 0.2. And you just have to stick with that policy for all time, right? You can't just sort of jiggle that policy partway through. Today, most fisheries use piecewise linear instead of just like a single constant value. So they might say, do a mortality of 0.1 unless the stock size gets like really small, and then you should shut off the harvest, or maybe you should ramp it down. But we explore relatively simple actions. We do this all the time, by the way, in papers as well, when we say, like, we kind of propose what might be action scenarios in these sort of very simplified ways. So there's sort of this scenario or that scenario. The RL algorithm is capable of a much more rich space of choices. So here, what happens in the scenario analysis, if you search for just the maximum mortality that maximizes the value, you get a value of mortality around here, shown by the green line, but the distribution shows the reward across a lot of replicates. And you can see that this is a very knife-edged policy. Sometimes it's getting much higher rewards. Sometimes it's getting much lower rewards. These are when none of the replicates collapse. And this is where many of the replicates collapse because you're holding it right on the knife edge of that tipping point. And that is not a good idea. The standard fisheries practice is to say we should be a little bit conservative. Don't do the maximum sustainable yield, but do a total allowable catch of maybe 80% of that. And you can see this is indeed, in this particular example, 80% is enough to kind of get you out of the danger zone. You're on average not doing that much worse. You never get these great rewards, but you never get the really low payoffs. So the reinforcement learning is able to take that same problem and always get the very high rewards. I mean, it can do that because it has a much more dynamic management policy. So here, many scenarios with maximum yield will yield an early crash, right? And so you get short of the total rewards. 80% mortality, you get kind of a constant abundance, but you don't get great rewards. The dynamic or the deep reinforcement learning approach here is allowing the population to have a much more dynamic oscillation. And as a result, it can pull back and not harvest when the population sizes are low, and it can increase harvest when the population sizes are high, and it can achieve that much higher reward with greater success. So does it work, right? You may have noticed in that early slide with the leaderboard, some of these methods are doing great and some are doing very badly, right? It's one thing for a method to work like in theory. It's very difficult to take it and into practice in general in the real world. And so, it's important to know the failure modes of this and not see it as a magic bullet. So one thing that you see happen here, this is another 2-legged robot learning to walk, and this is the convergent solution. It is getting reward for moving to the right, and it has figured out how to move to the right, and it is stuck in this pattern, right? It's very hard for it to learn a different way because this works, I'm getting my reward. So this happens a lot in real reinforcement learning as well, that your algorithms can be stuck in suboptimal approach strategies, and it can be difficult to kind of escape that approach. Another thing that can happen is that they can do solutions that aren't what you really wanted. And this often happens because of how we define the rewards in terms of math versus what we really think of as the incentives. So here is a reinforcement learning algorithm that's learning to play a computer game, simple game. It's a race boat. You want to go around the race course as fast as possible. That's what racing games do. Now, in order to kind of make the game a little bit more interesting, there's these little like green fuel pods. You can get points for picking up these fuel pods as you go along the race. So let's like see how our reinforcement learning algorithm goes around this course. So you see the arrow, the race course goes this way, and our robot is going the wrong way around the course. Ooh, and you lose points if you crash into something. So it has managed to find this one spot on the race course, ooh, crashing into things, where you can pick up points by grabbing those little fuel pods. And if it gets stuck in this spot, the loop is just the right length that those fuel pods repopulate just in time for it to get there. And so by doing the worst possible behavior, you can see its score is blowing past all the other racers, which are now racing around the course. It's the star and the other colored things. And so you get what you say you want and what you really want are not the same thing. And you can get these very weird results as a consequence. So these create some really interesting challenges, both to the application of reinforcement learning in the real world and in using that in conservation management. There's this nice recent paper from two students I have worked with, Millie Chapman in my group and Lily Zhu at Harvard in computer science, looking at the parallels between a rather old literature in ecology, adaptive management, Carl Walters style stuff, mostly established in the 70s, and it's being kind of rediscovered at the moment as the kind of grand challenges of reinforcement learning. So being able to deal with these different sources of uncertainty, being able to deal with systems where the environment itself is not constant, but changing over time. So non-stationary, non-ergodic situations. Being able to deal with cases where you don't get your reward until the end, right? Instead of getting lots of little rewards, you get some high payoff after a long period of time. These are common features of conservation problems, and they're very much the leading edge of the reinforcement learning in computer science, though currently these literatures are happening in completely separate areas. And so this paper is kind of trying to parallel many of those discussions and pointing out in some places we're kind of ahead in ecology, in some places we're kind of ahead on the computer science, and these two groups should probably talk to each other more. At the same time, we see that this is not just a subject of interest for academics anymore, right? There is probably not a big computers company on the planet that is not now trying to do some form of AI and do some form of that AI for what has been often called social good, right? That we can sort of make the world a better place, make the environment a better place. So these examples are from the AI from Earth, from Microsoft, Global Forest Watch from Google, and Global Fish Watch as well, also in partnership with Google, to carbon markets, to, of course, Marxan, to video-based learning of individual species for conservation goals. There's sudden demand now to not just do conservation that is based on computation in an academic world, but to go and put these things in practice. And so this raises some real questions for us in doing so, right? So this was the piece that accompanied the announcement of this talk. When I first joined this group that was from computer science, trying to look at what happens when we make real world decisions with these AI reinforcement learning. We had a workshop at the NeurIPS conference, the big AI conference in computer science, on the political economy of reinforcement learning systems. And I just thought that was a nice picture of the king. Of course, the social scientists who are helping us think about these questions of legitimacy and accountability all immediately recognized that as the frontispiece of Hobbes' Leviathan. And it turns out that if you go back and read Hobbes, he also thought a lot about reinforcement learning. He only believed in negative rewards instead of positive rewards, but basically that humans were reinforcement learners, and that you had to have the sort of the king with all the authority to come in and solve those problems. To put decisions into a political lens expands our space of understanding these problems sort of even more. So we saw that already I had been using RL to sort of put more ecology into the process, right? But what you can also realize is that what we think of as the objectives versus how these objectives will play out when they're not done by sort of a scientist saying, what's the best solution? But they're done by large companies saying, oh, I can choose harvest quotas for you. But now that creates not just a way of coming up with a solution, but it creates a lot of control for the possible outcomes. It's a transition of power from the traditional actors in a conservation space, the academics, government researchers, nonprofits, to now our tech sector, which is heavily involved in the details of those algorithms. And so we have a recent piece of work trying to explore some of the consequences of RL, not from a technical aspect, but from a power aspect. We started this question saying, is this what's the ethical thing to do with these decisions? And we were reminded by working with social scientists that we're kind of posing the question wrong, right? It isn't to ask is what Google would be doing setting harvest limits right or wrong, but to say, is this a transition of who has power? We tend to think of decisions only in terms of the decision maker, but there are many other indirect ways to influence outcomes. You can set the agenda. You can say, these are the action space, right? And you're only considering those actions. In fact, this is what we sometimes do as scientists when we choose these model choice problems that I began with at the very beginning. We say, here's my model, here's somebody else's model, and my model is better, right? We artificially constrain the decision problem to be choosing between one of those two models, when in fact, the real space of models could be much larger. We also have world-making power in when we say, this is what the environment looks like. These are the possible states that can go into the environment. These are the equations of motion for it to evolve, right? And that this sets only the space of possibilities, right? And if that is too small from the real complexity of the world, we can lead to very incorrect decisions despite having an optimal algorithm. At the same time as this pessimistic, there's a great concentration of power in the very few companies that could run these big algorithms that we were starting to fret out. I just wanted to highlight this converse example of what I would characterize as the unreasonable effectiveness of open source. So early on, running these big RL models that are in all of those Nature papers, you try to reproduce the results, and you're like, oh, you need about $300,000 of computer credits just to do the computation. That these very big AI models were concentrated in the hands of only companies that had that amount of computer resources. And what we have seen happen in the space of large language models in the past couple months is that once some of those models get out, they have gone in the space not of years or sometimes decades the companies thought it would take to scale these models down to be able to run. But here within a month of Facebook's model leaking, people were able to run the large language models on a phone, on a Pixel 6, right? That the open source community very quickly innovates. So I think it is worth thinking about maybe just because these algorithms are complex does not mean that they can only be controlled by very large companies. I think another aspect that we're starting to explore there is what underlies the actual data that drives these models. In this case, the data informs our fit to the environmental simulator, right? In that, if we read the language coming out of the social good space, we see data is highlighted as this neutral, objective resource for accountable and transparent decision-making. Data is the new oil, it's out there, we will take in the data, we will use an algorithm to make a decision. The algorithm is open source, so everybody can see it. What could go wrong, right? And in fact, as we look at the available data being used to train these environments or train these machine learning methods, we realize that there's a lot embedded in that data itself. Data is not, in the words of Jenny Goldstein, Eric Nost here, free floating in the world, waiting for conservationists and technology companies, but the data is infrastructure, which has embedded standards, rules, technologies, and environments that structure it. And there can be biases rooted in those, or assumptions rooted in how that data is collected that influence the kind of outcomes we get. And so this can just as easily get us those undesirable RL results as a badly trained algorithm. To give one last closing example, the Global Biodiversity Information Facility is probably one of the largest collections of biodiversity occurrence data, right? But if we look at where those data actually occur, we see that it is not so much at a world stage a map of global biodiversity in terms of total occurrences, or even in terms of species density, but a map of where cell phones are. Right, that we can see human densities. We can see Europe and England and the US and Australia lighting up most here, right? As we zoom in, we find that it is not just a population density problem. In the US, you can see cities and roads emerging, but you can find any pattern about humans in the data that is about every species but humans. In fact, here going into Los Angeles, for instance, you can, through the frequency of detections, you can figure out which areas in Los Angeles were redlined way back in the Great Depression, even though the practice of redlining, where immigrants and blacks were not allowed access to home mortgage lending at the same rate as whites was abolished in the 60s. The legacy of that process is still visible in the GBIF data. So the stories about how data is collected are reflected in the data itself. And so we need to be able to account for all of that complexity if we're going to make decisions based on that data. You can pull out humans conflict. This is Cambodia's GBIF records, and you can see these collapses in occurrence. It's observations were not the species declines, but were civil wars. So kind of any aspect you look at, you can see when humans go on holidays, when baseball games are, all in the GBIF data. And so the problem is quite complex and requires a lot more teasing out. All right, so just to close, we have seen several sort of large patterns emerging from these different examples I've jumped between, that a good forecast does not necessarily mean that it is a good decision. And in fact, even a good decision is not necessarily a good decision, meaning that you can get a high reward on the problem, but you're not necessarily solving the problem that you really want to solve. This is perhaps Goodhart's law that whenever you make something a metric becomes a target, it ceases to be a good metric. And so as we think of how do we do conservation in terms of setting reward functions for biodiversity metrics, sort of, are we optimizing the metrics of those outcomes? Are we really getting what we want? We have seen that context matters. So the actions and the rewards are part of that context. This kind of throw it over the fence approach that like science will do the job of coming up with good models, make good predictions, and then it's the decision maker's problem is too clean. Right? And the world is always more messy than that. We cannot draw this bright line between scientists and decision makers. We can take a scientific approach to finding good or robust policies, though, even when we can't make good predictions. We can try all possible scenarios, and we can say this agent manages to do a not too dumb thing in every one of these environments, or even in some cases, a very smart thing. How we come up with those different environments matters. In fact, one of those frontiers of reinforcement learning is this problem of what they call adversarial environment design. And of course, being computer scientists, they have a separate RL algorithm that goes and tweaks the environment in a way that tries to make the focal agent do as badly as possible, kind of discover its blind spots. I think that kind of approach can help us understand where our decision policies, where our rules of thumb are most likely to be able to be robust, given all that we don't know, and where they have blind spots or vulnerabilities. How do we move forward? I think building more environments lets us test the policies that we have. It's easy to build an environment because we don't have to give in to the constraints of, I need this to be able to work in a stochastic dynamic program. We can just write in an environment. We need to test those agents. As ecologists, we tend to always work on different problems. Everyone has their own problem, and the novel thing is most important. And in computer science, the incentives are almost too far the opposite way, that everyone works on exactly the same problem, and the goal is to move up a little bit better in the leaderboard. I think somewhere in between is a happy optimum, where we can have different development of common algorithms on common problems. We're not all working on separate problems, but we're also not working on only like the 6 big benchmarks that currently dominate the computer science space. And build collaborations. And of course, that's my thank you slide. And it looks like I'm also filled up the disk space, many collaborators and much funding. And this is obviously interdisciplinary work. And I think not just within ecology and computer science, but into political ecology and sociology, and these other elements that surround the problem. So thank you. I'll stop there. And I think we have a little time for questions.